Welcome to Two Projects. In this video, we are going to explain the project aircraft tracking based on an anti-drift multi-filter tracker in satellite video data. Before diving into the execution, let me give you an overview of the project. So, the project aims to upgrade aircraft tracking by utilizing video data, which is crucial for surveillance, air traffic control, and military operations. Unlike traditional methods like radar or manual observation, video data provides a more comprehensive and real time view of aircraft movements. Traditional tracking methods require significant manual effort and are prone to errors, especially in scenarios with high air traffic or complex flight paths. So, the project introduces advanced algorithms like anti drift multi-filter tracker, that is ADMFT, and YOLO, that is you only look once models. So these algorithms excel at detecting and tracking objects in videos and images even in challenging environments. So ADMFT is designed to handle the uncertainties of tracking objects in dynamic environments such as the sky. It employs advanced mathematical techniques to maintain accurate tracking under varying conditions. Coming to YOLO, it is a highly efficient algorithm for detecting objects in videos and images with speed and precision. It quickly identifies planes in video frames, contributing to the overall effectiveness of the tracking system. So, these advanced algorithms streamline aircraft tracking, improving accuracy and efficiency. By automating tracking processes, the system enhances situational awareness, facilitates faster responses to incidents, and ultimately contributes to safer and more efficient air travel. So, we will be building anti drift multi filter tracker and YOLO models for tracking and detecting aircrafts from images and videos. Now we'll look at the workflow. So the project starts by diving into the dataset containing satellite images and videos. These data are fundamental for training and testing the aircraft tracking system. Through meticulous examination and processing of these data, the project ensures a strong foundation for subsequent analysis and algorithm development. So each image and video in the dataset undergoes careful reading and processing. This step involves extracting essential information and features necessary for aircraft tracking. And various image processing techniques are applied to prepare the dataset for use with tracking algorithms. So, images are converted into blob objects, a format suitable for analysis by computer vision algorithms. Classes are defined to identify different objects with specific focus on aircraft. And bounding boxes are then declared around these objects to accurately localize them within the images or video frames. And conversion of color spaces are performed to standardize the representation of images, ensuring consistency across the dataset. Images are resized to a uniform dimension, facilitating uniform processing and analysis. Masks are created to highlight regions of interest within the images, aiding in object detection and tracking. So, after these steps, data augmentation steps like randomization, rotation, and transformation are applied. So, randomization techniques introduce variability into the dataset by applying random transformations such as changes in brightness, contrast, or noise levels. And images are rotated at various angles to simulate different viewing perspectives, enhancing the dataset's diversity. And transformations like scaling, shearing are applied to simulate distortions that objects might undergo in real world scenarios. So, through data augmentation strategies, the project aims to enrich the dataset's diversity and robustness. By exposing the tracking system to a wide range of scenarios and variations, including different lighting conditions, orientations, and environmental factors, the system becomes better equipped to handle real world challenges effectively. Augmenting the dataset is very important for training robust and generalizable tracking algorithms. It helps mitigate overfitting to specific data patterns, improves model performance on unseen data, and enhances the system's ability to accurately track aircraft in diverse real world scenarios. So, we will be training the models on the original images but from different angles so that they can generalize well to different conditions and situations. So, these are the image processing steps followed. So, after pre processing, the pre processed images are fed into deep learning models. The project employs state of the art deep learning algorithms such as ADMFT and various iterations of YOLO, that is YOLO V5, YOLO V6, YOLO V7, and YOLO V8 for detecting and tracking aircraft. So, different algorithms are assessed to determine their effectiveness, aiding in selecting the most suitable one for accurate aircraft detection and tracking. And a user friendly web interface developed with Flask and SQLite enables easy access to the tracking system, allowing users to register, log in, and utilize the system seamlessly. Following processing, segmentation, and detection, the system showcases segmented aircrafts with bounding boxes around the detected aircrafts on the original images of videos through the front end interface. So, overall, the project aims to create a advanced system using satellite video data to track aircraft movements, benefiting air traffic controllers, military personnel, government agencies, and researchers. By integrating advanced algorithms, the system enhances aircraft tracking accuracy and efficiency. Providing an intuitive interface makes the system accessible to various users. So, the system aims to improve aircraft detection accuracy in satellite imagery. The project's advancements improve aviation safety, security, and research by providing tracking, aiding in preventing collisions, monitoring airspace for security threats, and supporting research on air traffic patterns and environmental impacts. So, this is what we'll be doing in this project. Now, we'll look at the software and hardware requirements to execute the project. Hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application needed is Anaconda, primary language required is Python, front-end framework needed is Flask, backend framework needed is Jupyter Notebook, database required is SQLite 3, and front-end technologies required are HTML, CSS, JavaScript, and Bootstrap 4. Now we'll understand about the algorithms built. So these are all the algorithms built. First, we'll understand about ADMFT, that is Anti-Drift Multifilter Tracker. So it is an advanced tracking algorithm designed for dynamic and noisy environments such as satellite imagery. It employs Bayesian filtering techniques to estimate object states while accommodating uncertainties and variations in motion. So, this algorithm excels in scenarios with complex object motion patterns or occlusions, making it suitable for surveillance, robotics, and autonomous navigation tasks. Now, coming to YOLO. So, YOLO, that is You Only Look Once, is a computer vision object detection algorithm that quickly identifies objects in images by splitting the input image into a grid and simultaneously predicting bounding boxes and class probabilities. Unlike traditional methods, YOLO processes the image just once, making it extremely fast. It predicts multiple bounding boxes and their associated class probabilities for each grid cell and then removes redundant detections using non maximum suppression. So, this results in a final list of detected objects along with their bounding boxes and probabilities. So, these are different versions of YOLO. So, coming to YOLO V5, it is known for its balanced performance between accuracy and speed. So, this version relies on a backbone network called CSP Darknet 53. It utilizes focus modules for downsampling and path aggregation network, that is PAN, for feature fusion, enhancing object detection across different scales. YOLO V6 model introduces a key difference by using EfficientNet L2 as its backbone network. Compared to EfficientNet used in YOLO V5, EfficientNet is known for its efficiency with fewer parameters. So, YOLO V6 also employs a novel dense anchor box generation method to improve object detection accuracy. YOLO V7 uses a modified version of the Swin transformer architecture as its backbone. This architecture leverages self attention mechanisms, leading to better feature extraction compared to convolutional neural networks used in prior versions. Now, coming to YOLO V8, it is the latest version focused on facilitating performance comparisons with older YOLO models. So, YOLO V8 also introduces a unique loss function and an anchor free detection head, which are technical improvements to the overall detection process. So, this is about the algorithms which we have used. So, we have compared these models. After comparing these YOLO models, we have observed that YOLO V5 has outperformed all other models. So we have deployed YOLO V5 into the Flask framework for aircraft tracking. Now we'll see the execution. We'll be executing the project using Flask web application. So before execution, first we need to open the code folder which contains the project source code files. So this is the code folder and these are the contents I have in the code folder. This is dataset folder. So here we can see I have train, test and valid folders. I'm opening train folder. We can see I have two subfolders again, images and labels. I'm opening images folder. So these are the aircraft images I have. And in label folder, I have annotation files. So each annotation file corresponds to an image file in the images folder, providing details about the objects, locations, and classes within the image. So this annotation file corresponds to this image in the same way. This annotation file corresponds to this image. Similarly, each annotation file corresponds to an image file in the images folder. So these label files often follow the YOLO format where each line represents a detected object. So this is the line. So in this image, there is one object detected. So this line represents a detected object where the first column specifies the object's class index. This is the object's class index, followed by the bounding box coordinates of the detected object. So these are the bounding box coordinates normalized to the image dimensions. So this is the x limit, this is y limit, this is the width, and this is the height. Similarly, I have object's class index followed by the bounding box coordinates of the detected object in the other label files also. So these label files correspond to an image file in the images folder. So on these image files and the images, we'll be training the deep learning models. So here I have separate folders for train, test, and validation sets. So each serves a distinct purpose in the training and evaluation of the YOLO models. So train images are used for teaching the models to recognize objects. Coming to test images, they evaluate how well the models perform on unseen data. And validation images help fine tune the models for optimal performance. So in test and validation folders also I have images and label files only. So this is about the dataset. This is models folder in which I have model files which contain algorithm information. So these files will be loaded into the project code during runtime to utilize the trained models. This is static folder which consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is test cases folder in which I have images and videos on which will make the detections and tracking. This is app.py file. This .py file contains the information related to front-end logic. It includes coded in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And this is Notebook Jupyter source file, which contains a combination of code, graphs, and outputs all in one place. Jupyter Notebook allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. It stores information like user signup details. So this is about the code folder. Now copy the path of the code folder from the address bar of the file explorer. This is the path, copy it. Open Anaconda prompt. Use the command cd followed by space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. This command executes the Python script and performs a runtime check for any syntax error or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I usually prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. Here we can see sign up and sign in links. Click on sign up link. So if we are new users, we have to register ourselves first. Fill in all these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on the sign in link. So as I'm already a member, I'm clicking on this link. Here we have to give our credentials, username and password. I'm giving mine and click on submit button. So it has redirected us to the detection page. So now we have to upload any image or video here and the application will track and detect the aircrafts from the image or the video. Click on choose file button. First we'll upload from the test cases we have. I'm selecting this one, click on open. The image has been loaded. Now click on upload button. It will take some time to load. So this is the uploaded image. And here we can see all the airplanes detected. We can see the application has drawn bounding boxes around the detected aeroplanes. We can see the label here. Beside the label, we can also see a probability score telling us the confidence level of the application in labeling them as airplanes and classifying them as aeroplanes. Click on try again. Click on choose file. We'll try uploading this image. The image has been loaded. Now click on upload button. So this is the uploaded image, and here we can see the application has detected the aeroplanes. It has drawn bounding boxes around the detected aeroplanes, and we can see the labels, the classification, and beside the classification label, we can see a probability score telling us the confidence level of the application in classifying them as aeroplanes. Click on try again. This time we'll try uploading the video we have. Select the video, click on open. The video has been loaded. Now click on upload button. It will take a lot of time to load because it will check each frame in the video and give us the results. So here we can see the processing. So here we can see the aeroplane has been detected in the video. We can see the bounding boxes being drawn around the aeroplane, the moving plane. We can see the label, we can see the probability scores beside the label telling us the confidence level of the application and classifying it as aeroplane. So in this way, we can also detect or track the aeroplanes in videos also. We can see this aeroplane has also been detected. So that was the video. So we can also take images and videos from Google and execute the project. So we'll try that. Now we'll search for aeroplane flying videos. We can also take images from here. So I'll download this image, download the image, click on try again, click on choose file, select the downloaded image and click on open. The image has been loaded. Now click on upload button. It will take some time to load. So here we can see the application has detected the aeroplane. It has drawn a bounding box around the detected airplane. And here we can see the class label. Beside the class label, we can see the probability score telling us the confidence level of the application and classifying it as aeroplane. We'll try uploading another image. We'll try with this one. Download the image. Upload the downloaded image. So we can see the application has detected the aeroplane. We can see the bounding box drawn and we can see the class label. We'll try with some more images. We'll try with this one. Click on choose file, select the downloaded image and click on open. The image has been loaded. Now click on upload button. So we can see the application has detected the aeroplane. We can see the bounding box drawn. We can see the class label. And beside the class label, we can see the probability score here, telling us how confident the application is in classifying it as aeroplane. So in this way, we can also take images from Google and get the detections. We'll try with this image, one last image, download the image, click on try again, click on choose file, select the downloaded image and click on open. The image has been loaded. Now click on upload button. We didn't get the detections here. We'll try uploading another image. We'll try with this one. Click on try again, click on choose file, upload the image. We can see the application has detected the aeroplane. We can see the bounding box drawn. We can see the class label and we can see the probability score. Now we'll try downloading a video. I'll try downloading a video from here. I'll try with this one. Click on try again. Click on choose file. Select the downloaded video. Click on open. The video has been loaded. Now click on upload button. It will take a long time to give us the results because it has to check each frame. We can see that here. So here we can see the application has detected aeroplane in the video. It has drawn a bounding box around the detected moving aeroplane. We can see the class label. We can see the probability score beside the class label. So this is the video. I have downloaded another video from Google. We'll try with that also. Click on choose file. Select the video. The video has been loaded. Now click on upload button. It will take some time to load. We can see the processing being done. The application will look at each frame to give us the detections. So this is the video, and we can see the application has detected the moving aeroplane. We can see the bounding box drawn around the aeroplane. We can see the class label. We can see the probability score telling us the confidence level of the application in classifying it as, in labeling it as aeroplane. So this is the video. Click on try again. Now we'll look at the conclusion. So the project integrates advanced algorithms like ADMFT and YOLO to create an efficient aircraft tracking system. By improving accuracy and accessibility, it benefits stakeholders such as air traffic controllers and military personnel, enhancing safety and security. So, this solution signifies a significant advancement in aerial surveillance and object detection technology. Now, click on Logout.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.